Welcome everybody. Let's talk about reactions of alkenes. Alkenes are pi bonds, and pi bonds can react with electrophiles to give you different products. So the pi bonds here can snap and make bonds with things that need electrons. So the pi bond is a pair of p orbitals that coalesce to form a pi bond. Therefore, they're electron rich. The p orbitals have one electron per orbital. So therefore, when you have a pi bond, it tends to be a nucleophile. What does that mean? It loves nucleus, which is positive. So it's almost like just like you would think of an anion or a lone pair being a nucleophile, pi bonds are also nucleophilic. So they can jump up, and let's say you have an electrophile coming in. This is, let's say, a proton or a hydrogen plus. This is seeking an electron, and it just goes and says, wow, here you go. I can form a bond with this. So now you can form a bond with a hydrogen or an electron deficient species, which is what we call electrophiles. Okay, they love electrons. Well, once you do that, then you'll have an empty spot here because you have a p orbital here that's empty. In which case, you would have a nucleophile now coming in and then seeking it. The nucleophile would probably be a counter ion with this. It could be an HCl or HBr, HI, HOH, all of these things. Now, does it really matter whether the hydrogen goes here and the negative anion, like a chloride or a bromide, goes here? Can they be switched? Well, in this case, they can be switched because it's a symmetric alkene. How about a situation where you don't have a symmetric alkene? Let's take, for example, an alkene like this. Here is your carbon-carbon double bond, and you have, let's say, a carbon here with two hydrogens and a carbon here that's connected to two carbons. Does it really matter where the hydrogen goes? Does it matter whether it goes here on this carbon or on this carbon? Turns out it does. And sometimes 98% of the time when the pi bond pops, the hydrogen prefers to go on the carbon that has more hydrogens. Which means you're going to have your empty p orbital on the carbon here that's connected to more carbons. Why does this happen? Why does it really matter? Well, when you have a carbon plus, the carbon plus is electron deficient. It wants to have atoms next to it that can donate electron density into it. It wants to have friends that are going to give it some cash when it's down. Okay? Whereas a hydrogen really has only a 1s electron. It really cannot donate. So you don't want hydrogens on the carbon that has a positive charge. You want to have carbons. Carbons can donate inductively through the sigma bonds. They can also donate through hyperconjugation, and we talked about this when we talked about E1 SN1 reactions. So therefore, in this case, a tertiary carbocation is going to be a lot more favored than a primary. So you don't want to put the hydrogen on the carbon that has more carbons. You want to put the hydrogen on the carbon that has more hydrogens. That way you will get a highly substituted or more substituted carbocation. Now your nucleophile comes in and sees this, and it can attack it. Okay, so this is what we call Markovnikov rule, which says hydrogens tend to go on the termini of the alkene that has more hydrogens, creating a more substituted carbocation for the nucleophile to attack. Nucleophile can attack on top or bottom, but it always would attack on the carbon that is more substituted. Major product, all right? That is called regioselectivity. Okay, so I'm going to write that down because these are very important terms. Regioselective. What does it mean? It means bonds tend to form in a certain region of the molecule compared to other regions. So there is a preference for it to be like this. and not switched. That's regioselective. So if you take alkene reactions, we can classify them as regioselective and non-regioselective. So let me write that down. Non-regioselective is if it really doesn't matter where it goes, okay? And that would happen with other reagents, not with HCl or acids. Now, let's look at an example here to define that. Let's say you have an alkene just like this. You put in a hydrogen here. The hydrogen would go on the carbon that has more hydrogens. I'm going to write down these hydrogens just to illustrate that point. So you have an H plus. Your electrons are going to jump over and catch that. As we said before, pi bonds are loosely held electrons, so they tend to be the nucleophile. Hydrogen is electron deficient. It wants electrons. It loves electrons. It's an electron lover or electrophile. So when you see reactions with alkenes, a lot of them start off with a nucleophilic attack on an electrophile, and you will see that there's a lot. So here you go. Your hydrogen goes to the carbon with more hydrogens and forms a more substituted carbocation. And that is something that Markovnikov says. Markovnikov follows Markovnikov's rule. Markovnikov's rule says that when you have hydrogens attacking a pi bond, the H plus tends to go on the carbon that has more hydrogens, creating a more stable carbocation, which is then attacked by another nucleophile. In this case, let's say the nucleophile is a halogen, chloride minus, electron-rich species. So that is going to then attack your more substituted carbocation, forming a alkyl halide. So this is something that you will see with a lot of the acids and also with water and acids. Now let's look at some of the things that could happen within a regioselective reaction. So it could be Markovnikov, or it could be regioselective and be anti-Markovnikov, hydrogen going to the carbon with more carbons. So we can classify regioselective reactions as Markovnikov and anti-Markovnikov. Now, when you have, let's say in this case, when you have a Markovnikov reaction, you can have it so that every single time the nucleophile is either on the same side as the electrophile or it's on the opposite side. That is called being stereospecific. If you only got this every time, or you only got this every time, that's called same side would be syn, opposite side would be anti. If you tend to get only one of this, that is stereospecific. All right? So what about this case where you added H and Cl? The chloride here can attack on top or at the bottom. All right? So you can have chloride up and down. In this case, we have an achiral center. Therefore, it doesn't really matter. But if it were a chiral center, you would get a 50% R and 50% S. That would be non-stereospecific. All right. So if you can have Markovnikov reactions, and within the Markovnikov, you can have stereospecific, where you only get attack in one direction, or you can get non-stereospecific, where you can get attack on both sides of the carbocation. The carbocation is sp2 and flat. The p orbital can be attacked from above or below. Therefore, you can have stereospecific or non-stereospecific reactions. In this case, where you have an HCl, you don't get a stereospecific reaction because you have 50% chance of attacking up and 50% chance of attacking down, because this is a perfectly flat carbocation. Therefore, this HCl addition will fall under non-stereospecific addition. So not just HCl, you would also have HBr, HI, and so on. Also HOH addition and HOR alcohol addition. Both of this would have to come with H2SO4. I'll just put H plus for now. All right, or H3O plus, which is a better way of writing H plus. So we can also have stereospecific Markovnikov reaction, which means you have a regioselectivity. That means it prefers one side over the other, and in addition, it prefers one direction over another direction. Why? Because of the way the reagent molecule is and the electronic forces guiding the nucleophiles and the electrophiles coming in. So let's talk about stereospecificity. Stereospecificity means that the mechanism favors a certain stereoisomer over the other due to the direction of attack. It could be syn or anti, typically. All right? So an example for that would be, let's say you have a cis alkene, a cis butene, and let's say you add to this bromine. Now, bromine doesn't randomly add to the double bond anywhere and any which way. It always adds on the opposite direction. So if one is up, one is down. And since this is a chiral molecule, you could also have the exact same molecule in a mirror form, a mirror image of that. So this and this, these two are enantiomers. Now in this case, you get a perfect one-to-one mixture. So there are two main ways that the mechanism adds stereospecificity. One is called anti-addition, like this, where they're on opposite sides, or syn. These are the two that we are going to look at in this chapter. Now, in addition to this, there are reactions where you don't get a perfect one-to-one mixture. You get one of the enantiomers or diastereomers more than the other. That it would be called stereoselective. So stereoselective is the other term that we want to look at today. Stereoselectivity is when one of the stereoisomers is formed in a much larger quantity than the other stereoisomers. For example, if you have two stereoisomers that are enantiomers as the product, one enantiomer is formed in a higher amount than the other. Or if you have two diastereomers as your product, one of the diastereomers is formed in a much larger amount than the other. So there is a preponderance of one of the stereoisomers, and that is called stereoselective. Why does this happen? Due to steric and electronic reasons within the starting material. So a certain stereoisomer would only give rise to a certain type of stereoisomer. All right, so let's do an example for this, and let's do an example that is a very famous example by Sharpless. So contrary to what his name says, he is a very sharp person, and he came up with this and got the Nobel Prize for it. This is a reaction where you have titanium isopropoxide, and you have a chiral reagent here. Depending on the chirality of this reagent, you would have one of the stereoisomers, the enantiomers, being the major product and the other one being the minor product. In this case, the methyl up and the CH2OH being down, this is going to be about 98%. Its mirror image is going to be about 2%. So if you hold a mirror here, you would have this methyl going down and the CH2OH coming up. This would be 2%. This was a huge breakthrough at that time because most reactions would give a racemic mixture if they were enantiomers. You would also see a lot of examples like that when you have diastereomers. You can have diastereoselectivity. One diastereomer is formed in a much larger amount than the other due to steric or electronic reasons within the molecule. So all these three govern the reactions of alkenes. So if you have regioselective and non-regioselective here, let's look at some of the reactions that are going to be stereospecific and non-stereospecific, and those are going to be, as we just said, anti or syn. So we are going to incorporate regioselective stereospecific reactions into alkenes. This chart is what we're going to follow all throughout this chapter for alkene reactions. So as we said before, nucleophiles and electrophiles can choose to react in a certain region of the alkene as opposed to any other region, and that is regioselective. Or it could have a random addition. That's non-regioselective. Within the regioselective, we can have Markovnikov, where the hydrogen goes to the carbon with more hydrogens. Or it could be anti-Markovnikov, where the hydrogen goes to the carbon with more carbons. So those are the two types of reactions that we're going to see in the regioselective reactions. Now, within the Markovnikov reactions, you can have a reaction that's non-stereospecific. That means it can go up or down equally. And that would be with the acids, water and acids, or alcohols and acids predominantly. There are other reactions, of course, but these are just the ones that we're considering for your class. Okay, there are a lot more reactions than this. So that would be the non-stereospecific. Now, within the Markovnikov reaction, you could also have stereospecific reactions. For example, after you add a bromine or a bromonium, you can open it up in a stereospecific way with water or alcohol. Same with halogens and, let's say, some acids. So we're going to look at those reactions. Now, these are anti. That means they're going to attack on the opposite side of the initial electrophilic addition. So within the Markovnikov reaction, when you add mercuric acetate, there's an initial syn addition that's then followed by an anti-addition of the nucleophile. I could have very well written that out here. Okay. Now, anti-Markovnikov reactions. We are going to talk about borohydride additions, BH3 additions. Okay. That is going to be the reverse of the Markovnikov rule, where the hydrogen goes to the carbon with more carbons. We are not going to have any anti-additions on the anti-Markovnikov reactions just for this chapter. We are going to have non-stereospecific reactions where you can have attack from above and below with peroxide and HBr, and that would be a radical reaction, which we will cover when we talk about radicals. Non-regioselective, that means the nucleophile and the electrophile don't really have a preference for either termini of the alkene. Those can be syn and anti if they're stereospecific. The syn reactions are quite a few. There are about 6 of them that we're going to be talking about. Osmium tetroxide, potassium permanganate in base, hydrogen platinum, epoxidation with MCPBA or a peroxide, diazomethane, and also ozonolysis. Ozonolysis initially a syn addition, which is then scrambled and lost during the reaction. We would also have a non-regioselective reaction that is anti-stereospecific with bromine and chlorine in an aprotic solvent. So there is a difference when you have halogens in aprotic versus halogen in protic. And we would discuss the reasons using the mechanisms of the reaction. Now, you could also have non-regioselective, non-stereospecific reactions, and we are just going to talk about combustion. And you probably have done combustion in general chemistry, which is just breaking up the molecule with oxygen and releasing carbon dioxide and water. So these are a slew of reactions that we're going to talk about in chapter 8. And let's get started with the non-stereospecific Markovnikov regioselective reactions, which are hydrohalogenations of alkenes. So I will see you soon with hydrohalogenation of alkenes. Talk to you soon. Bye.